Hello and welcome. This is lecture 6 on encapsulation. This is a special encore presentation because a live recording unfortunately did not include audio. However, we still have the chat log, so I can still try my best to recreate some of these questions in live time. So, as a reminder where we are, we've been kind of incrementally covering a little bit of Scala, a little bit of Chisel, and then doing a little bit of hardware design and kind of learning all three at the same time in order to kind of do our Agile approach. And we're going to keep doing that. So if you remember at the beginning of this week, we took a big leap and learned about how to do state elements like registers and such. On Wednesday, we learned about collections, how to start having groups of things together. Today is about encapsulation, really kind of how to include things. And really this is one of the most kind of important themes about good design, not just for hardware design, but even good software engineering is how do you choose to draw the lines around things? Like what goes where? How do you factor things? How do you group things together? And this is really kind of one of the things you can have the biggest impact on how easy or hard it is to develop your thing you're working on, as well as for others to work with it, right? Where if you have good abstractions and you encapsulate all the complexity for something inside of itself, people can use your component without needing to fully understand what's going on inside. That's the goal, right? And also, ideally, the way you've chosen to define that component and how to encapsulate it, what's there, is a good unit for people to reuse, right? It's the right interfaces, the right functionalities, etc., right? And this, speaking very generally, this is true for both hardware and software. And so, in today's lecture, we're going to cover some of those mechanisms available to us. Particularly, we're going to cover some of the Scala functionalities first, so we know it's kind of possible in language, and then we'll talk more about how to use these actually in Chisel and actually to make our designs more or better encapsulated, right? And so how we use these, how we choose to break things up and group it, that's more of a design skill, and we continue to come back to that and reflect on that in talking about these sorts of things. In particular, to be more concrete, today we'll be covering some features in Scala, like how to do simple method calls, as well as recursion, a little more about how the object-oriented stuff in the language works. And then we'll start talking about how to use these within our Chisel modules, and of course include something called bundles, which is yet another encapsulation tool available to us. So let's go ahead and load in our notebooks. The notebooks, as of last night, now support Chisel 3.5, so that came out this week. It's a nice big feature release, and we took the opportunity to jump to it right away. There's some great features. It'll actually impact this lecture's content in just a few slides. So, first let's start off talk about Scala methods. So you may have seen these kind of implicitly, but maybe now let's talk about it more head-on. So in Scala, to define a method, we simply, say def, and then give it a name, and then an argument list, right? And we say equals, and then what it does, right? So in this case, we're taking a simple method that takes in an integer and adds 1 to it. And so that's the code for it. And you can see, of course, we can define it, and then we can invoke it, right? And so if we evaluate this expression, we say, yes, plus 1 on 5 is going to be 6, right? And the result of, even defining the method in the first place is we define this function. Great. Now here it's a simple one-line function, so I took the opportunity to go ahead and just declare it all in one line, but of course if you have multi-line functions, you're going to need to use the curly braces. This works just as well. But sometimes for really simple functions, this is nice to do it kind of like the way I just did it. Now to kind of cover a little more about what's going on, these arguments to a function are immutable by default, so they're kind of like val. And if you want to, you can actually have multiple arguments and make some of them optional, meaning if a user does not provide the second argument in this case, it's going to use a default value of 1. So you can see with this plus x method, which is very, very similar, we just want to be a little bit more parameterized. With the plus x one, there's this x parameter, which, if we give it, it's used. So 5 plus 2, we get 7. However, if we don't give it, it's going to use that default value of 1. Right? And another thing to note about these functions is that you don't see the return statement anywhere, right? So this is once again, remember how if statements, we said the last line, the either if clauses is returned. Same thing's true for these functions where, if I was to do something internally, maybe go ahead and, do some other val, whatever, doesn't matter. The last line is the thing returned, and so it's kind of an implicit return. You can use the return keyword, but you don't need to, and you shouldn't, and it's usually recommended against it in style guides. And so, this is kind of how you can do a simple method or function in Scala. Now, I want to remind folks that in these examples, here I am writing methods wherever I want. I'm invoking code wherever I want. This is not the normal Scala behavior if you have a proper compiled Scala project. This is normally these things need to be inside of either a class or an object, right? However, because we're using this almond environment, almond is a way to kind of get the REPL-like behavior inside a Jupyter notebook, we're able to have this much quicker way to access the language and get the ball rolling, but normally we have to have things inside of either an object or a class. But cool, so here we have a simple method. Now, with methods, of course, naturally we might want to do recursion. And so we covered how to do iteration earlier in the week with for loops, and we kind of said, if you need to do some things, you can kind of squint and, use a for loop with a var, a mutable variable. Well, with recursion, we can avoid the need for that, right? We can kind of tuck that need for mutation actually into the fact that we're calling the same function over and over again, but changing the value of the arguments going into it, right? So by invoking the function multiple times and each time having a different value for the arguments, we're kind of effectively mutating that variable in a way. And that's actually a much cleaner way to kind of reason about it and test it. So in some ways, arguably, this is going to be much better, right? So let's talk about how to do recursion in Scala. Well, there's not really too many tricks to it. You just have to call yourself to be a recursive function. That's not hard. There's actually one more detail. And that is, if I don't give a return type, it's going to tell me I need to give a return type for a recursive function. So the way you give a return type is you annotate it with a type, right? And you can see, okay, yes. So there's, I've annotated this as type return int. And so maybe you're wondering, well, what happened on the last slide? I don't think I saw that. That's right. We didn't bother with return type because it was able to infer it, right? We said the input was an integer, and we added 1 to it, so that's going to be an int. So of course I could be extra careful and verbose. Sometimes it's good for readability to be very clear about your return types so folks know what you're trying to do. Okay, so yeah, it's a returns integer works great. It's also a way to kind of check yourself, right? Imagine maybe you're writing out this method and you meant to return a string, and oh wait, no, that's not a string, it's an int, right? It's a type mismatch, right? Another one of these things, of course, in Scala, we're trying to make what would be runtime errors into a compile time error, right? Here we're kind of doing more strict type checking. If we leave it off, we're doing type inference and hopefully we're doing the right thing. But if you want to be more kind of double check yourself, you can say, this should be an int, and let the compiler check to make sure, yes, the thing on their side actually is an int. But for recursive functions, we are forced to give a return type because otherwise we don't know what the return type is. And then, of course, as typical practice for writing a recursive function in any language, right? You have the recursive call, you're calling the function again. But you also, if you want this to end, you need to have a base case in which, under some conditions, it doesn't call itself anymore, right? So, initially, we're called with some n. We keep calling this function over and over again recursively, but if we're reducing the n, at some point, n is going to reach 0, and then at which point we are going to return 0, and we are not going to recurse anymore, and that's going to kind of back out, right? And so you can see, of course, like I said, there's no return statements here. It's just this function returns the last line of this body, and while this if statement is going to be evaluated, n compared to less than or equal to 0, and then it's going to return, whichever thing is the path is taken, right? And so either return 0 or n plus recsum. So it's a very nice, tidy thing. So what does recsum do? Well, so recursive sum is adding up the numbers from 0 to n, right? So, for example, if we run it real quickly on this little example, recsum of 4, 0 plus 1 plus 2 plus 3 plus 4. Yes, that is 10. Cool. And what else can we do with it? Well, there's a classic, recursion example. We do something like Fibonacci. So we can, of course, write that. This isn't the most efficient way to compute Fibonacci, of course, but if we solve it recursively, yes, I can find the current number in a sequence by considering the prior two, and this, of course, is going to branch out inefficiently, but you can see, yes, we can do Fibonacci no problem. And hey, I can even call my function once for different sizes of numbers. I can basically reproduce the entire Fibonacci sequence. We'll go ahead and comment that out. And you can see that, right? So it's very helpful, very useful. You've probably seen recursion in other courses, but here we are doing it in Scala, and it works very nicely, very naturally. The compiler can do smart things like optimizing for tail recursion when that's possible, etc. So make sure we don't miss anything. Oh yes, one more thing. So when it comes to return types, you may be saying, well, wait a second. What if there's no actual thing in returning? I just want to repeat multiple times. Well, if you're just repeating multiple times and not returning anything, why are you running that code? The answer is you're probably having some sort of side effect. Maybe not great from a style or point of view, and also not very functional in terms of the functional programming style, but still possible, still able to do that. The return type for that is unit. So unit is kind of this like, void type, so to speak, if you need to have something that doesn't return anything. And so let's say you will have a function that's not even recursive. Let's say you just call a function to print something. So it doesn't return anything because it's printing to the console. That's the side effect of, putting text on the console. So that one, when you write that function, yeah, you probably give it a unit. When you actually declare one of those, you don't even necessarily need to have the equal sign. You can just go like that. Cool. Okay, let's keep going. So we've covered just a little bit about Scala having these methods and how you can use them recursively. So how are we going to use them within our Chisel designs? Well, remember, really all we're doing in hardware design with Chisel is instantiating hardware components and connecting them together. That's it, right? All the stuff we're doing in Scala, we're able to kind of make this wonderful program around it, is us kind of choosing, well, what are we instantiating and how are we connecting it? And so methods provide a really nice way of encapsulating that functionality and behavior. Because really we're encapsulating Scala code. We're actually encapsulating a program, and just these programs that we're making a very deliberate purpose of having, to create struct hardware, right? And so why do you use functions, right? The usual reasons, number one, you can encapsulate complexity, right? Someone can just call your function not knowing fully how the things works internally. Also, sometimes it's a good way to kind of somewhat give intuition of what your code is doing. If someone sees a 10 line block of code, to kind of look at it and think, oh, what's going on here? Maybe you have good variable names. If you have a good function name, someone may have a pretty good intuition about what you're trying to do in that code. They actually don't need to read your functions, well, especially if it encapsulates that complexity, right? They can just go ahead and keep going. So it's a really good way to kind of not just make your code more tidy, but also easier to understand and simpler to reason about. Also, of course, if you declare a function, you can declare it once and then use it multiple places, right? So if you find yourself copying and pasting code around your design, whoa, that's, in any programming language, that's something, it's a moment you should take a pause and say, wait a second, if I'm copying and pasting code and changing like two things or changing no things, I should probably put to some sort of shared code location function method, subroutine, whatever you want to call it, and, reuse it, right? And then, as we just covered, recursion is a great way to kind of break apart bigger problems into smaller problems that are more manageable, and it's a nice way for us to kind of get some of these iteration-like behaviors we want without having to use mutable variables. So that's nice. And so although I've been kind of telling you, yeah, you need to put Chisel components inside a module, that's not quite true. To fully evaluate everything, they need to be in a module. However, you can definitely declare things as long as they eventually find their way inside of a module, you're good, right? So for example, we're going to see an example in just a second of declaring Scala functions that are a Scala function, but it returns a Chisel component, right? And then that function will be called within a module, and then it'll have that Chisel component instantiated inside that module. So we'll see that in just a second. Okay, so if you remember from our last lecture, we talked about building this kind of not even last lecture, on Monday, about how we could build a shift register, delay line, whatever you want to call it. It says n registers in sequence. One's input feeding the next one's output. This is a code we had from before. And so you can remember you decided the various options with the tools we had available at the time. Maybe using var in a for loop was actually reasonably clean, right? So we use this var to kind of track the last thing we connected to, and then every iteration in this loop, we create a new thing. It connects this input mode to regenex syntax. This creates a register. And with using regenex, it's kind of this shortcut, right? It creates a new register whose input is connected to whatever is passed in the argument. In this case, that's the last connection we want to do. And then the result of regnext is a register object. We can use that, and when you refer to that, you get the output, right? So we're going to remember, kind of use this last column as like a pointer and kind of pointing to the last register we made. And then as we go through this loop, we keep creating new registers and then pointing to that one. And eventually we connect that to the output, right? And so we've seen this work. It works pretty well. Here we go. And you also might notice that the Verilog is a little bit simpler today, none of that extra stuff. The other stuff that was there before was actually needed to simulate well, but for making it easy to read for lecture, we're able to kind of suppress that. It's one of the nice features of new Chisel 3.5. But you see the functionality here, right? We have our two registers, and they're filling through. If I had more registers, we can kind of see that pipeline behavior more clearly, right? It's kind of going through it. Okay, so this is what we did previously. here we are using var in a for loop, or mutable variable, I should say. We could do the same functionality with recursion, right? So don't need to use the var anymore. So now what happens is we're going to call helper n times, and each time we're either going to perform that connection. When you call regenex, it's making a connection to lastCon, and eventually we're going to pass on lastCon. So this helper function is basically going to do all the work and basically create that thing for us, right? And so yes, this will produce the same hardware. Maybe I'll go ahead and make it the same depth. And there we see it, right? So the naming's a little different because of the way the under the hood Chisel is deciding to infer variable names for things that aren't named in design, but you still see the same structure. It's still 4 registers passing in a line, right? And here it's nice, right? We don't have this var, and we're using recursion. Now we can use recursion in much more sophisticated and elegant ways. This is just kind of a first example. And like I said, remember what we're doing, right? We're using all this Scala fluff to choose what we're instantiating and how we're connecting them, right? So remember, regenex is instantiating a register. Next kind of as that shorthand to also include one connection when you're creating it. And then we're also making connections like places like here, right? And so we kind of perform all those connections. So yeah, we're instantiating registers and connecting them. And we happen to use in this recursion to kind of organize this because as we just saw, right, we can change this parameter and very fluidly change the depth of this shift register. Cool. So normally I'd pause for questions, but of course this is an encore, so we're flying. Now that was using a method to help out. Let's talk a little about the object-oriented system in Scala. So you might have seen us use this class keyword, especially when we're declaring modules, right? Usually we declare a module by making a class and extending module. And in most languages, when you hear the terms class and object, they have certain meanings, right? In particular, usually class is like a type, and object is an instance of a type, right? And people often say things, oh, this is object-oriented programming. Scala is object-oriented. It has classes. The one wrinkle is that the word object has a slightly special meaning. It's actually a keyword. So when you see a class, that's a type. That's what you would normally think of an object in most other languages. You can declare it, you can instantiate it, you can instantiate n copies of it. They can be different, no problem. I'm going to try to use the word instance for an instance of a class. Rather than saying, all these objects, I'm going to say, no, it's a class and you instantiate instances. And the reason why is this object keyword special in Scala. So what does it mean in Scala? Well, it's what's called a singleton object. That means there's always exactly one instance of this object. And the way to think of it is, your program starts, the object already exists. And it exists until your program ends. There's not really any construction or, deletion, right? It's just always there. There's always exactly one. And so there's going to be a lot of reasons why we want this. And interestingly, sometimes we're going to want to have one of these singleton objects working in tandem with a class. So they're both going to have the same name. And we're going to refer to that object as a companion object. And they can kind of have this nice symbiotic relationship where we're going to use the class and we're going to make instances of that class to actually do the things we want to do. And we're going to kind of use the object to kind of do a few things, right? We can use the object to hold shared state. Like maybe we want to track something about all the instances that are out there. Additionally, we might want to use that object to provide constructors. And we'll cover that in just a moment about how we can have various different flavors of constructor to make it kind of nice to construct things that we want in a certain way. It's referred to as a factory method. A third use of objects is simply, as I said a few slides ago, you can't normally have methods just floating around anywhere. Let's say you have some methods you want to call. These methods are stateless. They have no hidden variables. Every function, every argument you give to them is the arguments they use to compute, and that's it. As long as it lives somewhere, you still want to kind of encapsulate and organize it so your code is structured, you can toss those into an object, right? Because those functions are stateless, right? They're not attached to any kind of state or any variables, and so to associate those with a class instance would kind of be a waste, because then you kind of need somebody to instantiate the class instance and then work on it. You don't have to do that, right? You can go ahead and just put those inside of an object and kind of have an object that's really just a bunch of code pieces that are stateless. That's also totally fine. Okay, so let's talk our way through this code snippet here. So maybe first I'll go ahead and comment this out so it doesn't get us distracted. So if we aren't trying to build a module, even just a simple class in Scala, what do? Well, we define our class, we say class to give it a name. And remember that the entire body of the class is evaluated when it's instantiated, right? So yes, we can have things like method instantiations, but we can also do things like, it's almost kind of like a constructor is the entire body, right? So you can go ahead and say, hey, I was made, right? And so when someone instantiates that, it's going to get called. And, when you validate this entire class body time instantiated, you're also defining functions associated with it, or methods, right? And so you can see, for example, that, okay, we define this pair class. It's got A and B. We can call sum on it. So yeah, we called sum. We got 7. Interestingly, in Scala, if you have a method that takes in no arguments, you can actually call it without the parentheses, right? So that's also valid. And this might seem like an odd simplification, but there's kind of true reasons for it. Number one, as an embedded DSL, or hoping to support embedded DSL, Scala does this to allow people to have more native syntax. And we'll see some other syntactic tricks Scala does to make that more possible. But number two, it also is a good way to kind of convey intent, right? Where if you have a method that takes in no arguments and doesn't change the internal state of the thing you're working on, from the outside, as a user of that object, that instance, forgive me, it may not be easy to tell the difference between a field, like, that's that val inside there has this value, versus I'm calling a method that computes the result I want, right? From the outside, it doesn't really matter, right? All I care about is I'm using that name to get something, and I get something, and as long as it doesn't change the internals, whether it's a function or, accessing a field, shouldn't really matter, right? And so that's kind of why they simplify things and kind of make that encouraged, right? So if your thing doesn't take any arguments and doesn't change the internal state, yeah, go ahead and leave off those parentheses and make it kind of nice and straightforward. Okay, so what else are we talking about for these classes? Also, of course, when you want to make an instance, you got to use that new keyword. Hey, I want a new instance of this class, and it evaluates the entire thing. Okay, so that works, right? But you can imagine that there is you want more, right? So what more would you want, right? Well, maybe you want to instantiate without using a new keyword, or maybe you want to overload a constructor. If you're sitting here going, wait a second, if I have to give all the arguments like this, maybe I can make some of those arguments have a default value, and I can make myself get a little bit of flexibility. But what if I really want to have overloaded constructors? How could I do that? You actually can do that with the companion object, right? So let's go ahead and uncomment this code. Oops, forgive me. There we go. Okay, so for companion object, what are we doing? Well, we're doing a few things. So at a minimum, we are providing a factoring method, right? So if someone says my pair and gives arguments, it's going to call the apply method. And the result of this apply method, if you look at it, remember, returns the last line is, hey, a new instance of my pair. So actually, even though it's a special factoring method, it's calling new for us, right? And what's nice about doing this is we can go ahead and, design this class to be, trusting that the arguments are called correctly, and it provides all the arguments. However, you can imagine you can put some intelligence in these constructors inside of your factory methods to actually handle various cases and to make it kind of handle the way you want. Additionally, you're using the opportunity to track how many instances have been made. So in this case, we're tracking how many there are, and so this is a var, so I'm allowed to mutate it. And actually, if you have shared state inside of an object, you're going to be forced into having mutable state, right? Because normally for a class, you can make the class immutable, that's fine. And if someone wants to change the value, they just make a new instance and copy the parts they want to keep, and they change the part they want to change, right? So it's still immutably, it's made a new instance. Well, with a singleton object, there's only one instance always, it's the same instance. There's no creation or destruction. So if you want to change something about it, you have to have a mutable field. So yeah, if you have this in state there, it's one of these kind of places you're forced in a mutable state. Okay, but yes, here we are tracking how many pairs have been instantiated, right? So, you can see, for example, if I go ahead and run this code, maybe we don't need to see the partition up here anymore. I'll go ahead and hide that. But you can see, okay, so let's say this is actually creating an instance, right? It's because it's calling this method, and it's returning a new my pair, and we can call .sum on that, no parentheses because there's no arguments, no problem. And we can see if we want, for example, query how many pairs exist in this object, how many pairs have been created. Originally there was 0, now there's 1, so we've made one, right? If I go ahead and want to create another instance, notice here I'm using a different argument pattern, so I'm calling a different constructor, no problem. And actually, in this case, we're going to go ahead and reuse our first constructor and just substitute in 0. Cool. We can call someone that, and now we can see, for example, now there's been 2 pairs created. So the question is, maybe you may be wondering, well, how do we get this binding of, this thing, or I should say this thing, associating with this? Well, in Scala, apply is a key word. It's special, right? So what it does is when you have an apply, it says, if you ever have like an instance or an object and you immediately follow it by parentheses and there's no, function name in there, that triggers the apply method, right? And so, for example, this apply method, it can be in the companion object. It can also be in a class, right? So, for example, you could imagine, like, let's say someone, defines a string, right? And let's say you want to get a character at a certain location. You can do that, right? And so what's this doing? This is calling apply on that string instance, right? Because, there's no .func in here, right? It's just directly doing it. So apply is what you invoke when it happens. So because apply is a reserved word, you can't have a method called apply. Sorry. But you can see how this kind of works out, right? And so with this, we're able to make these this companion object and use factory methods, right? So a lot going on, a lot of keywords, right? But you can see what's going on. We have this nice class we like. We can make instances of it with the new keyword. However, we can also use this companion object to kind of tidy up a lot of the parts about instantiating it, accessing it. If there's certain constraints that need to be made about these input parameters or certain intelligence required about, we can take this argument and change it this way to make this other argument or whatever. You can put a lot of that in these factory methods, right? And, especially if you imagine more complicated systems, you perhaps want to, remember other things that have been created and reuse things or et cetera, et cetera. These are great ways to kind of insert that in there. So it's kind of a nice layer of indirection, so to speak, in a construction process you can use to do cool things. Cool. Okay. I'm going to pause for questions in the encore version, but here we go. All right. Let's keep going. So what are we going to use this object for? Well, it's a nice thing to kind of work in conjunction with our class, right? So if you remember the counter example we had in our prior lectures, we showed various ways to create a counter, and one of the bodies we kind of liked was this when syntax. It was kind of very unambiguous what's going on. If you also remember, we had this discussion about, it was very nice about, what if, our maximum value is, a power of 2? Can we really be clever and avoid the need for comparison and just trust the binary numbers naturally wrapping around, all that stuff? Yeah, that was a wonderful conversation. But let's look at it again today. Okay, so we have our counter from before, and this is the same. However, now we can go ahead and let's go ahead and first run this code, right? And so if we want to look at this Verilog for it, there's still some line info here, but we can kind of see the core functionality, right? There's a register, and for resetting, it's set to 0. Otherwise, if we're allowed to change and we're below our limit, we do this connection. This connection is the thing plus 1. Otherwise, we need to wrap around to 0. Okay, so here we instantiate an instance of our module. Remember, so now if we look at our code again, let's remember our module is really a class we were defining, right? You keep defining all these modules, but we're actually just defining classes. These are kind of, the arguments to them. And we extend module, right? So Scala is object-oriented. It has an inheritance system. And so by extending module, we kind of, are bringing in a lot of stuff that kind of makes us reasonable for Chisel. We'll cover extensions a lot more later in the quarter, but for now, you can kind of just remember, okay, if I want a module, let's extend that. Cool, so this works just fine. If I have that companion object, which we just defined down here with this factory method, I can now get an instance of this module without even saying new anymore, right? It looks very similar, just no longer needs a new keyword, because that companion object is kind of taking care of stuff for us, which is cool. All right, so that may not seem like a big advantage, but we'll start seeing some additional gain possible with these factory methods and companion objects. So we just showed counter as a module, but now let's take it a step further, right? What if we made a counter as just the bare snippet of Chisel, and that way someone can instantiate a counter inside their design without needing to instantiate a full module? So maybe a natural question might be, why am I so afraid of modules? Nothing's wrong with it, but we're thinking about how the design turns out. Remember, modules kind of has very strict rules, but I need to have I/O, and modules will appear in the fertile and the Verilog. Now, a good, hardware design flow, your CAD tools will, optimize across module boundaries. However, at various stages of human reasoning about the results, as well as, debugging and just talking about things, modules still kind of represent an important level of abstraction and kind of encapsulation. And so, as I said in the very beginning of this lecture, right, one of the biggest things we're going to be doing is thinking about where are we drawing the lines between things, how are we kind of grouping things together. There will be times where we will want to appreciate the nuance of different types of lines between things, so to speak, right? So there's encapsulating things in a method, which is perhaps a weaker form of encapsulation than encapsulating things in the module. And so by having kind of this weaker form of encapsulating things, this is actually very beneficial. So we can incorporate, many functions incorporating small snippets of Chisel without having to go as heavy as a full-on module. So let's look at this. Okay, so here we declare it. So you're still declaring a class. We can even do this inside a function, but for now we're doing it inside a class. What does it do? Unlike the things we've seen so far, these are, this is a Scala variable. This is a Chisel thing, right? So normally so far we've had parameters to our functions and to our classes and modules. They've all been 100% Scala, right? Right, int, whatever typically. Now we're blurring that line. Now we're taking in a Chisel thing, right? Remember, bool is the Chisel one, boolean is the Scala type. So we're actually taking in a Chisel thing, which is kind of crazy, right? And then here we have the body of that counter, right? So we have the register, which we initialize, and we use our enable signal, which was passed in as an argument to this class instance, right? So when someone instantiates this class, right, it evaluates this body, and so it's going to go ahead and evaluate this body. So yes, I'm going to create account, which points to RegInit, and then use a when statement, etc. So now for someone to actually be able to use this instance, they could call new themselves, but it would be best to go ahead and wrap that with a factory method. So in the companion object, we're using that apply. Still the same argument list, but we're going to do two things. We're going to go ahead and instantiate it for them, but then we've just created this set of Chisel circuit, right? We've created, register and a couple muxes and an adder to kind of choose the next value to counter. How does someone else work with that? Well, really what they want is they've already given as an input the enable signal. Clock and reset are implicitly connected, so you don't need to worry about those. But really they kind of want the output. They want the count. They want to know what the value is. And so, yeah, we're going to return this, right? So what is this? This is mc.count. So this is, from this instance, the count field, right? And the count field is a register. And really when you refer to register like this, you're referring to the output, right? So in other words, someone's getting the output of this register, which is the count. Cool. So we can go ahead and, run this code. And if we want to instantiate to kind of play around with this and see how things are fitting together, we can totally do that. Like I said before, we can have code inside Chisel inside not modules, but eventually needs to find its way into a module, right? If we go ahead and so now here we are instantiating this module, but notice how even inside this module, we're actually instantiating our counter is just my counter. Remember, my counter is looking at namespace. What does it find? It finds my counter as a class, my counter as an object. Like this, it's going to know to use the companion object, and it's going to call apply, and it's going to match up. Okay, so you can see, yes, here we have a Scala variable coming in this way to parameter for the width, and then this Chisel thing coming in, right, which actually is connecting it over here. And remember, this whole thing returns instances as class, but this returns instance to the class, but this is actually going to return just that field, that register, and that register happens to be connected to a circuit involving those muxes and the adder and such, and that's going to kind of get passed through, right? So we're kind of creating this snippet of a Chisel graph. I think of, okay, here's a register connected to a mux, connected to another mux, connected to an adder. That snippet, we're only pointing to just the register. We're going to pass that over and connect that to the output. Cool. So yeah, we can go ahead and run this, and we can get our counter Verilog. Looks like the same Verilog we've been seeing in the last few examples. That's all right there. So cool. So here we've now started creating Chisel outside of a module environment. Here we're still doing inside a class body, but we actually do inside a function body if you wanted to. Using this factory method to kind of tidy up the invocation of this and the accessing of this. But you can kind of see now there's becoming a little bit more of a continuum of how we can kind of blend Chisel and Scala, right? Where before we kind of had purely Scala functions and then these Chisel modules, and we're very deliberately making a Chisel module that has Scala arguments for parameters, but internally is all Chisel. Now we're kind of blurring it. We can have maybe a Scala method or a Scala class that returns some Chisel art pieces. We can actually take in Chisel pieces as arguments, they're first class citizens, and that kind of stuff. So you can kind of start seeing a little bit more of that flexibility. Cool. Okay, so like many programming classes, we have students build very basic components over and over again, data structures, whatever. And it's important to remind students that despite us reinventing the wheel, that we are reinventing the wheel, right? So you should use standard library components when they exist. So when it comes to this counter, guess what? The Chisel standard library has a counter, and it's actually really great. So you should use that counter. But we still might keep using this counter as an example to understand the internal just because it's simple and easy to explain. But when library components exist, it's a really, really, really good practice to use them, right? Why? Well, number one, that's code you're not writing, right? Why rewrite something that already exists? Two, hopefully if the standard library is any good, is correct, right? So that's just less things for you to get wrong, right? But there's actually some additional benefits, right? Another benefit is if someone's reading your code and they're familiar with the language in a standard library, that's something they can understand much more readily, right? Where if you reinvented the wheel and they kind of, even if you have good naming, to appreciate, okay, that's their version of a counter, okay, and go from there, right? But they know this is a standard library counter. I know what a standard library counter does. Boom, they're reading your code faster. And then finally, a lot of times standard libraries, people spend some time optimizing them, and they can do some pretty nice tricks automatically. So you really want to use standard library stuff when it exists. Even something like a counter, you're thinking, oh, a counter, it's a counter, right? Like, aren't all counters the same? Why would someone be confused by saying my counter versus someone else's counter? If I call it a counter, it's obvious it's a counter. I would disagree, right? There's some nuance, right? There's a little differences. So let's say, for example, let's try out this standard library counter. So we, went ahead and instantiated it. And you can see actually this counter, has that, we kind of know from the outside now, we know a little bit about Scala, we know this was the result of a factory method, because you can see we're just kind of calling on this object. That's cool. But actually it doesn't just return the value, it's also this wrap signal. So that's already kind of, wait a second, I thought I counted just a number. So now it's actually kind of letting you know when it wraps around, which for some applications is actually what you care about. You care more about the fact that it wrapped around than the fact what the actual number is. But if we go ahead and look at the Verilog, okay, we get some Verilog coming out of here. Now, it's a little bit confusing with all the extra commenting there. But if you look at the key portions, you'll recognize, okay, yes, there's the +1. It recognizes this wrapping when this current value is 3. And okay, well, if we're resetting, the value is zero. Otherwise, if we're enabled, we're going to assign the +1. Wait a second, there's no comparator here for like that case we were talking about before of determining a max value wrapping around. Guess what? The standard library is optimized, right? So we were talking about last time how if your limit's 1 less than the power of 2, it'll naturally wrap around, and so they can avoid the need for that comparator, right? So if I go ahead and change this, you'll see that now it will be looking at the result of comparator to see if it needs to wrap around, right? In particular if it's reaching a max value. But the thing I want to point out is not just reaching a max value, is what's the semantics, right? Actually, with the Chisel counter, the value isn't the maximum value, which is what we've been doing in our example. It's actually the number of things you want. So if I ask for a Chisel counter with 4, you're saying I want to count 4 things. Under the hood, it's going to count 0, 1, 2, 3. But the maximum value is actually that 1 minus that, right? Versus our counters, we've been kind of giving the maximum values. So you can see already, even if something is innocuous as a counter, there's some subtle but important differences in how they're used, right? So once again, using standard components, someone else comes in and they don't need to spend so much time pulling hair out thinking, oh wait, is their counter inclusive, exclusive, where is the start? That kind of stuff. Use the standard counter. What's also cool is they actually have other variants, right? So for example, if we look at this other version, we see that instead of requiring just enable signal and a limit, it actually takes a Scala range. And so go ahead and run this, and pretty cool. So we can see it's doing like a +2. So in this case, taking a Scala range and turning that into a hardware device, right? So it can be an arbitrary range. We can say, counting by 2, or you know what, maybe I want to say, hey, I want to go from 6 to 3 by -1. Okay, let's go ahead and turn that into hardware, right? So we're taking these arbitrary ranges and just turning it into hardware. That's pretty far out, man. So that's possible because, we have this nice helper function. So I keep saying standard library. Maybe it's a good time to click on this link right here. And let's go ahead and go there. And so this is the Scala doc for Chisel. So you can find links to this on the course homepage or just web search for Chisel 3, documentation. So yeah, so there's Scala doc generated documentation on these Chisel components. So for example, a counter, we're looking at it right now. And it's worth noting that, it's telling you this one's actually not even in a module. So we're just talking about building Chisel outside of modules. This counter is an example of that, right? So it's generating the logic directly. No internal module is created, right? Keeps telling you does not create a Chisel module. You can see, you already saw both versions, right? You can see that there's the kind of the wrapping version versus the range version. You can see it has various fields. But cool. So we've been talking about that, and then now that we've kind of covered some code, let's actually look at the code, right? Let's go one step further. So here we are in the source code for counter in the standard library. So you can see that, counter is implemented as a class, and it takes actually in things as a range. We'll cover what options are later in this lecture, but you can kind of see what's going on, right? There's, some notions about what's going on. A lot of what's going on here, especially with any robust hardware design, especially a library component, a lot of checks on the parameters, right? Making sure they meet certain constraints and make certain assumptions, but also communicating to the user that, hey, not only does this parameter not meet certain requirements, give them helpful information, right? Tell them why you can't work on this, right? It's a really important step, right? Improve usability by making it, kind of check well. You can see a lot of things going on here. You can also, for example, if you see very carefully, remember we talked about this whole power 2 optimization? Well, here it is down here, right? Here's that is pow 2. Remember we kind of discovered that ourselves with help of the TA last lecture. And that's all there. So you can kind of see the increment feature is here, and it's wrapped up with a lot of this Chisel functionality inside methods. It makes it kind of easy for people to kind of reason about it and look about it. So this is a counter class, right? But we were calling that syntax directly, so we know it was kind of a companion object without even actually seeing the source code, right? And so now here's that companion object. We can see that these various constructors are available, right? So there's an apply with just a number of things to count. If we actually want to pass in the enable signal, we can do that too. And notice, this is taking in a Chisel bool. Or does that more sophisticated constructor is also here. So these are all kind of here. So, as you kind of get more and more sophisticated this course, you'll be able to understand every last line, every piece of every code base, but the portions you'll understand will keep increasing, right? And especially these library components, which are using Chisel rather than the most advanced features of Scala to implement the tools themselves, they actually are quite readable, right? But fortunately, or hopefully, you can often read these documentations and avoid the need to go digging, right? And you can see there's a lot of other components available, and we'll be covering many of these throughout the course. So let's get back to our counter. Okay, actually, before we move on, I want to briefly recap. So we kind of been talking about this theme of how do we choose, how we group things together and encapsulate things, and we kind of have this variety of tools available to us, right? On the Scala side, we have, functions, classes, and objects. On the Chisel side, really we just kind of have modules and but we can kind of work in tandem with these Scala constructs to kind of make it more fluid, right? And so depending on the components you're working with, you probably develop your own intuitions. We'll also continue to discuss in this course about, maybe this functionality is best included inside a function versus included inside a module, included in a class, etc. But we kind of have these options, right? And the purpose of this course, especially so far, is we're just trying to kind of keep covering things. It doesn't mean because we cover something once, it doesn't mean we won't come back to it later in more detail. But for today, we wanted to kind of cover these encapsulation constructs, in particular, class, object, functions, and kind of show some examples in Chisel, but we'll continue to use this information to make, better encapsulations, better designs, better organizations as we go through. Cool. So in the spirit of that kind of encapsulation, there is another unit of we can work with, which is called a bundle. And so far, you've probably seen this without thinking about it. If we go back a few slides, as kind of just boilerplate. I've often kind of told you, sometimes there's code you just got to kind of copy paste and don't need to worry about. This is one of those examples, right? So, every module needs to have an I/O field. If there's no input or output to a module, why does it exist? And you need to mark that as I/O, and you have this bundle. Well, bundle's a special thing. So what's a bundle? Well, a bundle's a class defined in Chisel. Normally, we've seen like in the prior slide, you're instantiating, or you can do it here as well, you're instantiating an anonymous bundle, right? So you're just saying, hey, I want a bundle that has these fields. A bundle is really just a collection of things that are named, right? So it's kind of like a struct, right? It has a named set of things in there. But you can make bundles not anonymous. You can actually define your own classes by extending bundle, right? So here we defined the class mag, perhaps short for magnitude. And yeah, so it has a field M. And cool, that field M has, it's a 4-bit uint. So now I'm gonna go ahead and define my own module. Let's call it out module or out mod, whatever you want to call it. And takes in the Scala number and it assigns the output to that thing. Notice now when I declare the I/O, I'm just saying, hey, give me an instance of this mag bundle, because eventually for our I/O, we want to have a bundle in there. And we can make anonymous ones like we've been doing so far, or we can define it, right? And the reason why it's nice to define it like this is we can use it in multiple places, and we can also do some nice things by extending things. We'll cover in just a second. And so when you think of bundles, right, it's not just about I/O, it's really just a way to group things together. So you can definitely use bundles in a lot more places than you might expect. Inside the module, never cross the module boundary. And it's nice sometimes to be able to declare them once and use them in many places. One question or replay from the chat was, what happens if I, instead of making a module, I can make this a bundle? Those are different types, right? So a bundle is kind of this collection of things that are named, right? So a bundle is not just a collection of things, but also has names, right? In this case, I'm assigning a name M. We've seen vec, which assigns indices to its elements, and they also need to be homogeneous, right? So a vec needs to have things that are all the same type, but a bundle can be, mixed things, and they can give them, names. But a bundle still is kind of its own class on its own, and yes, we're extending bundle, but it's still the one, super class or parent class, right? Scala doesn't allow multiple inheritance, so something is of, a descendant of bundle, it can't also be descendant of module. So module and bundle are distinct. And so really for, lots of components, we need to have a module eventually. So, this needs to be a module. So that way we can actually, instantiate this, but a module can include bundles both for IOs as well as internally. And yes, we can go ahead and run this code snippet and it kind of does what we expect. We defined our, bundle externally, but used it here and we got this module. Cool. And yeah, we have clock and reset, like I said, during every module, even if it's purely combinational. For some of these examples, if we really wanted to do a quick hack to make it go away, we can bypass the addition of clock and reset. And yeah, there we have that stripped down module. I wouldn't worry too much about using raw module most of the time in your designs. Module is just fine. And remember the CAD tools are going to easily recognize the opportunity to prune off clock and reset, and they're going to do it. And it's not going to cost you any hardware in the actual product. Cool. Okay, so that was just kind of a hello world on bundles. Let's see if we can actually do some more sophisticated stuff with them. Well, we can extend bundles, right? So we saw that already, like a mag example. We can go ahead and extend it, right? So we have a magnitude. Well, maybe we want to make a type that's assigned in magnitude. So we're going to extend this magnitude class we just made. And so when you extend something, you get everything in that parent class, right? So even though it's not written here, this also has the field M in there, right? So if we have a sign mag bundle, it has both M and S as field elements, right? So this is an important thing to consider, right? Is that when you extend things, on the one hand, it's nice because you get all this functionality included. On the other hand, you've complicated reading the code a little bit, right? Because if someone reads this and they're looking at a sign mag object and keeps saying M, where the heck is M? They need to recognize that it extended something, and they also need to read that code for the other thing, right? So if, for example, in your design, people are only ever going to use sign mag and not mag, you should just put M inside here and be done with it, right? But if there's cases where you want people using both of these things, both mag and sign mag, both variants, and you want to save code, this makes sense, right? But like I said, it's one of these things kind of consider readability where extending things is really nice to kind of reuse things, but it does kind of decrease the linear readability of code, right? You can't just kind of look in one place and see things linearly in order where, no, now you need to jump around and do things, right? And it's another one of those things where having help from an ID can help. If you're looking at, let's say, code elsewhere, and you're like, wait a second, what's this field? You can click go to implementation. That code viewer will take you to implementation. It might be a class you thought it was, so maybe some parent class that, defined that field you're thinking about. So, reason 10,000 to use an ID. Okay, so you can extend them. You can kind of keep building up stuff. You can put them in Vex. You can also put Vex into them, right? We already saw that previously. In the prior lecture, we showed Vex having a variable number of ports. That was an example of a Vec inside a bundle. You can put bundle inside a Vec too, so you can go both ways. So maybe we want to make a pair of sign and magnitude numbers. And so yeah, we'll have two elements and they're of this sign mag. So now in our tiny example here, what we're going to do is, we're going to, this is all just to show the code running. We're going to make this interface, which is, going to be a pair of these sign and magnitude numbers, taking advantage of all this code. And, to connect it all up so we have, nothing unconnected and we can run it, right? Okay. So yeah, we can see, for example, it's going to, assign the output to be, A and B or 3 and 4. But the key thing is, yeah, these bundles can kind of be used all over the place. We can, nest them, extend them, etc. Cool. So this would be the point normally in lecture I'd tell you about something called clone type, where, because Scala's Chisel's embedded DSL, sometimes there's things we can't quite do the way we would like to do. And so we have to kind of write some boilerplate to kind of remind ourselves the fact that we're at the right valid Scala programs. So there's something called clone type, which you had to include in all of your bundles that were at least a little bit sophisticated. You know what? We don't have to anymore. There was a recent change. One of the reasons why I really wanted to get Chisel 3.5 going as soon as it was available fully is they've done work under the hood to remove the need for this. So before you had to include this kind of ugly thing, clone type, every time you had a bundle that wasn't super trivial, no more. And so the reason why I let this slide in here is I wanted to both highlight this and also applaud the developers, because this is nice. This is making the code more readable and better. So yeah, we don't need to worry about clone type anymore. But if you look at older Chisel, which most Chisel is written before 3.5, so you're going to see this plenty. You see this clone type? Yeah, it's boilerplate stuff. It's not something humans really wanted to write, but they kind of had to in order to make this type system happy. But no longer necessary, which is awesome. Good job, Chisel dev team. Cool. So with these bundles, what can we do with them? We can do a couple things, right? So one thing we can do is we can connect an entire bundle at a time. So rather, connecting this wire to this wire, this wire to this wire. You look at a lot of large designs, that's often what you're doing. You have very big designs, very big modules, you have really long input and output lists, and you're kind of connecting billion things together. Well, with bundles, you can do a few things, right? You can declare an interface once and reuse in multiple places. You can define interface in parts, right? Like, oh, I want to define the signals associated with an AXI port. And I can now, to have an AXI port, I can just instantiate that bundle rather than to worry about, less copy pasting, more tools doing things for you. That's what you want to kind of reduce errors and speed things up. With this approach of kind of using bundles to kind of simplify stuff, you do something called a bulk connection, where it's going to connect the entirety of two bundles to each other, right? And this bulk connection operator isn't just about connecting two bundles that can be exactly the same. It can also connect bundles that, one might be a subclass of the other, right? And so the subclass might be adding more fields, but connecting to a superclass, it's going to connect the fields it can, and it's also going to recognize that other fields are disconnected and prune them, but it's okay, right? And so this is kind of like you almost look like a smart connect operator rather than just bulk connect. So here's that sign and magnitude example from before. Like I said, in this case, maybe we know we're not going to use mag by itself, so go ahead and declare sign and magnitude in the same scope, right? No need to separate them out. And we go ahead and we have here sign and mag, and now we have this module which simply just passes through, no changes, just showing it, and we can say, yeah, we can connect the input to the output. Now, the thing about bundles is that they just hold a bunch of fields, right? They don't all have to go in the same direction in terms of thinking these as wires, right? So in this case, they do, right? In this case, both of these are going in the same direction, but the way it's declared, there's no direction given here. They're not called input or output. They're just fields, right? To make this IO, we need direction, right? We need to know these are inputs, these are outputs, right? Even though a wire, is a simple metal thing, in terms of the intent of how the hardware is being used, it doesn't need to have direction to it. It needs to know this is the output being read by, input, etc. And so, yeah, we mark it as input and output. It does the things for us. You can see the assignments there. In this simple example, if I didn't have the bolt connect available to me, I could connect each field individually. If I forgot to connect a field, it's going to complain that something is uninitialized. In this simple case, it will probably let me actually use the connect operator, which sometimes will work. Well, if you don't misspell it. However, like I said, you can have this bolt connection option. It's kind of like a smart connection thing, where like if there's a more sophisticated thing that needs to be done, make the connections work out, it'll figure it out. Cool. And so sometimes you'll see code where it just kind of pops up, and yeah, now you know what's going on there. Another thing you can do is this directionality issue. So we talked about before how not all wires in metal need to be going the same direction. So let's say, for example, I declared a bundle called handshake, which represents data going one way, and the receiver is saying, I'm ready to receive it, right? Okay, so with this handshake, I'm declaring one side is input, one side is output. Now, if you think about it, it's all a matter of perspective, right? That from one side, this is input, this is output. From the other side, it's output and input, right? And so they're flipped, right? And so there's actually this flipped operator lets you kind of flip a bundle, right? So, same pass-through functionality, just now we've given directions to the fields of the bundle. And remember on the prior slide, we declared that the entire thing is, either all input or either all output. In this case, this bundle is going in two directions. One wire is going one way, one wire is going the other way. So you need to flip it, right? So one side needs to be input, one side needs to be output. And you know what? Sometimes you have to take a second to pause yourself and think, okay, take a piece of paper, draw a box, and say, okay, I want this wire coming in, this wire going out, to kind of remind you from a certain module's perspective what's input and what's output. But in terms of kind of bundles kind of changing direction all at once, this flip thing's very handy. You can imagine what the code's gonna look like. Oops, well, we're gonna get it restarting, or I might have to actually manually restart it. Do I have to manually restart it? It forgot how to do Scala. So let's go ahead and re-import the library. In live time, here we are fixing stuff. So let's go ahead and rerun these commands. While it's happening, so we're gonna get our bundles back. And hopefully this will work again. And it does, great. Okay, we're back at it. Cool. Let's keep going. So, as a final thing I want to talk about is something called Scala option. So an option type is something that's not unique to Scala. Some languages have this, but maybe not everyone's seen it before. So what an option is a way to mark if a thing is valid or not, right? So it's second nature for many people programming that sometimes when you're initializing a variable, you want to kind of note the fact that it's initialized with somehow empty in some sense. So for example, maybe you have a null, right? Or maybe you make something -1 as an integer to kind of indicate it's not been populated. But all those kind of solutions programmatically are kind of taking a value from the final variable space and using that to kind of be a special meaning, right? That I know that null means it's not been initialized. I know that -1 means it's not been initialized. Option is a way that's kind of a little bit cleaner, where you can say, you know what? I don't need to take that element out of that space of representable things, and I can mark if it's populated or not populated, right? So an option takes in a t, it says t some type, and it either is none or some, meaning there's something there or there's nothing there, right? There's a lot of ways to work with option. There's some that are very graceful ways using functional programming. For today, we're going to kind of jump in using if statements. Not the cleanest way to work with it, but it'll be okay. So let's kind of go through this, right? So here we defined an option wrapping around int, and we say, hey, it has some value. It's a 4. So now if I want to work on that, and someone gives me this O, and let's say I know it's an option, but I don't know if it's populated or not, well, first I need to make sure it's populated. So I can call .isDefined. And if it is defined, then I can grab the value by saying .get. If it's not defined, well, it's empty. So we go ahead and run this code. You can see that, yes, originally I say that the value is sum4, so I can grab the value 4. If alternatively it was none, it'll recognize it's empty and say none. Cool. And then so you can see this being used, right? So a question that came in from Chisel, checking my notes again, was what's the difference between none and unit? They both seem to kind of represent nothingness. They both do. That's definitely right. They're actually different types for a reason, right? So none is a special thing associated with the option. So none means that option instance right now doesn't have a value, but it could at some point, right? The reason why it's an option rather than something like a guaranteed int or a unit means it's an option, right? You don't know. It could be a value, it could not be a value, right? There's some potential there was something there, or could be something there. Unit is like, not only is there nothing there never can be anything there. It's like empty, void, there. So yeah, we use unit, talking about like non-existent return types. There's a few other places will crop up. But none actually it says the result of option. And indicates that, currently right now there's not anything there, but hey, maybe you had another instance of option, there would be something there. Cool. Okay, so how might we use this in Chisel? There's a few ways. One of the best ways, or one of the funnest ways, is to have an optional field in your I/O. So here we're defining our own bundle, right? We're extending bundle, making our own. We have this field X. It's always there. It's an output. But now we're deciding, you know what? I know this field Y that maybe is there, maybe it's not there. And we're going to determine that with this has Y thing. So remember, Boolean is Scala. So this is a Scala parameter that's going to change the existence of Y. So, well, what is Y assigned to? Well, Y is assigned to, if, it's true, we're going to have a Y, right? So we're going to have, an output of, with type uint of n bits. And we're going to call that sum, right? Because it's an option type. So we need to say it's a sum. And if has Y is false, we're going to go ahead and mark it none, right? And so it's not going to be there, right? So we look at the code that uses this. So perhaps somebody's making this module that, is just spitting numbers out. And we have the same parameter, use Y in here. So it's going to go ahead and pass us to the I/O to change the I/O. And, if that field does or does not exist, it also needs to connect it or not, right? So if we go ahead and run this code snippet, we see initially that, yeah, we said has Y is true, so it includes Y in the I/O, and it also, does this code down here and actually connects Y. Alternatively, if I say, Y is not there. And boom, it's completely cleanly removed, right? It's not in the I/O, it's not in the module, it didn't exist, right? So a response might be, oh, that's pretty cool, but without option, couldn't I just do something like, hey, if has Y, let's have a val Y equals, this thing, right? Wouldn't that do the same thing? No, not quite, unfortunately, right? So there's a few things to point out. One, maybe I should put curly braces here so you understand what's going on, that this Y is defined within the context of that thing, right? So that's an important thing to kind of keep in mind. But additionally, right, that if Y is true, okay, this will work out probably, maybe. If Y is not true, then what happens, right? Because other places might refer to it, or at least compile to it. And so by having this option type, everybody can kind of agree that the existence of Y is a possibility, but just if Y is none, a lot of these things kind of will gracefully go away, right? And in particular, actually in this code, you could use the same Boolean variable to kind of track, if this thing should exist, or you could even check, is it actually in the I/O, right? You could kind of, reflect on yourself. Hey, is this I/O I'm creating a module for? Do I even have this field? If I don't have this field, I need to worry about it. But if I do have this field, I should connect it. Okay, cool. So that's how you might use this in Chisel. And that's a pretty nifty feature. Okay, and then one last little detail. We talked about seek on the last lecture. So we talked about how seek is immutable. And so if you want to put certain values into a seek, you need to put them in there at construction time. So you can, manually give them in, when you're creating it, hey, I want to seek 1, 2, 3. You can use .fill to get, 4 copies of 0. There's one more option. You can, of course, also make seeks by appending on the prior seeks. We saw the example in the code. There's one more way, which is this .tabulate. What this is going to do, it's going to call a function n times. I wrote it n is, in this case, 4 times. Now, for this function, it's right here. This is what's called an anonymous function, or a lambda. We'll cover these in more detail in coming lectures. But for now, just realize that, it's going to validate that code snippet as it goes through it, right? So, it's given a single argument, the index. In this case, I say 4, it's going to be 0, 1, 2, 3. And then what do I turn it into, right? So you can say, well, in this case, I'm not changing the index. We can just see the indexes come out. Or maybe I'm going to multiply them by 2. And so this is kind of 2 forms of that lambda syntax. This one is, inputs to the result. This other one uses this wildcard replacement, where actually, rather than to kind of have both sides, you can just kind of directly say, hey, that one argument you give me, I'm just going to use it right away. These wildcards, this underscore, really powerful. Makes the code a lot more concise, but there's times where you can confuse yourself, or times where you need to use a variable more than once, in which case you can't do it like that. But quickly run the snippet. You can see, yeah, I can declare a seek directly. I can fill it. If I do tabulate with just I get this. If I double it, I get that. Right. Cool. And so, yeah, so there we have tabulate. So that might be helpful in the coming assignments. So as a reminder of where we are assignments, we had lab 1 due earlier in the week. Homework 1 was delayed a little bit, getting the 3.5 functionality in there, but it's up, it's available and running Chisel 3.5, and that'll be due early next week. And then lab 2 we posted later today, and that'll also be due next week. Cool. Well, with that, I'll wish you all a happy weekend, and talk to you later.